Have you ever really stopped to wonder how the smart devices all around us actually, sense things? How does your phone know which way is up? Or how does a smart speaker hear your voice from clear across the room? Well, we're about to go on the incredible journey a single piece of data takes all the way from the physical world into the digital brain of a machine. And believe me, it's way more fascinating than you might think. No, really. Think about it for a second. How does that thermostat on your wall know the room is getting chilly? What's actually happening inside a robot that allows it to see and navigate around your living room? It's not magic, not at all, but it is this really elegant process that all starts by giving our technology its very own set of senses. So let's dive in and see exactly how that works.
All right, so this brings us to the first part of our journey. We have literally engineered ways for our devices to see, hear, and feel the world around them. And you know what's cool? The whole concept is surprisingly similar to how our own bodies work. Let's break that down.
This is such a great way to think about it. Just like our eyes detect light, optical sensors do the exact same thing for a camera or a self-driving car. Our ears, they pick up sound and vibration. And yep, so do acoustic sensors in our phones and smart speakers. And our skin, which senses pressure, touch, and temperature, well, it has its direct counterpart in the tactile and thermal sensors that make everything from robotics to weather stations even possible.
So, what is a sensor, really, at its very core? Well, it's a device that does one supercritical job. It detects some physical quantity, like heat or light, and it translates it into a language that machines can understand, an electrical signal. You can think of a sensor as the fundamental gateway between our physical, analog world and the digital one. It's the very first step in making the invisible visible to our machines.
And this is a huge deal. This sensor data is literally the food that feeds our modern connected world. It's what allows systems to monitor conditions, to automate processes, and ultimately to make intelligent, data-driven decisions. From all the smart gadgets in our homes to critical systems in robotics and healthcare, sensors are the absolute foundational building blocks.
Okay, so we've got our sensors, they're ready to perceive the world. Now let's get into the nitty-gritty, the next stage of the journey. How exactly does a real-world phenomenon get captured and turned into a signal? This is where we go from the world around us to a tiny electrical current in a wire.
So before a sensor can do anything, it needs something specific to measure. In engineering, we call this the Measurand. It's just the simple term for the real-world, physical thing we're actually interested in, whether that's the temperature of your coffee, the ambient light from your window, or the pressure of your touch on a screen. All sensing begins right here, with something tangible in the real world.
And this can be pretty much anything you can imagine. The temperature in a room, that's a measurand. So is the brightness of the sun, the sudden motion of a person walking by, or even the concentration of smoke in the air. Now, these are all physical properties that a digital system can't understand directly. So, how do we bridge that gap?
This is where the sensor's job as a transducer becomes absolutely crucial. Now, transducer might sound a little fancy, but it's just a word for something that converts one form of energy into another. In this case, it takes the physical energy of that measurand, like heat or motion, and converts it into raw electrical energy. Like a tiny change in voltage, this is the very first act of translation.
Okay, but here's the problem. That raw electrical signal coming directly from the sensor, it is almost never clean or perfect. It's kind of like a rough diamond that needs to be cut and polished before you can see its true value. And that brings us to our next critical stage, cleaning up the signal. Just look at the challenges here. A raw signal can be incredibly weak, just a few thousandths of a volt. It can be full of random electrical noise from the environment, kind of like static on an old radio. Its response might not be a nice, predictable straight line either. In this raw state, the signal is basically unusable for making any kind of reliable decision. So how do we fix it?
The answer is a process called signal conditioning. Think of it as the essential cleanup crew, and it's the hidden secret that allows even cheap sensors to be incredibly reliable. First, you've got amplification, which boosts those weak signals so they're strong enough to work with. Then, filtering gets rid of all that unwanted noise. Level shifting adjusts the voltage to the exact range our electronics expect, and linearization corrects any weird curves in the data to make it predictable. Every single step is vital to turning a messy, raw signal into clean, reliable data.
Now that we have a clean, stable, and predictable analog signal, we have reached the most critical bridge in this entire journey. It's time to meet the digital translator, the component that takes us from the familiar analog world of waves and flows into the purely digital realm of ones and zeros.
This bridge is called the analog to digital converter, or ADC, and its job is pretty much exactly what it sounds like. It's a translator.
It takes the smooth, continuous language of the real world, our clean analog signal, and it converts it to the discrete black and white language of computers, numbers.
And it performs this translation in 3 really clever steps. First is sampling. Think of it like a super fast photographer, taking thousands of tiny snapshots of the signal every second, capturing its every move. Second is quantization. Here, it looks at each snapshot and rounds its value to the nearest predefined level it knows, kind of like sorting those photos into a limited number of labeled boxes. And finally, there's encoding, where it assigns a unique binary number to each one of those boxes. And just like that, a smooth wave becomes a stream of numbers a computer can actually read.
So the data is now a clean stream of numbers inside the machine. We're done, right? Well, not quite. See, numbers by themselves aren't very useful. Now begins the final, and I think the most intelligent part of the whole process, taking that raw data and making it smart.
This is where a digital processor, like a microcontroller, takes over as the brain of the operation. It's here that those raw numbers are finally interpreted back into real-world units we can understand, like degrees Celsius or meters per second. The processor can fuse data from multiple sensors to get a much richer picture of the world. And most importantly, it's what makes decisions and controls things in the real world, like turning on a fan, sending an alert to your phone, or steering a car. This is where the magic really happens.
And right here, we can see how this all comes together. On the left, you've got the hardware, the microcontrollers that do all the thinking. And on the right, you see what they create. That processor uses temperature data to intelligently decide when to turn on a smart fan. It fuses data from an accelerometer and a gyroscope to perform the kind of complex motion tracking that powers virtual reality. This is the moment that data becomes action.
Okay, so let's take one final step back and look at the entire journey, from start to finish. We're going to put all the pieces together and trace the path of a single piece of information, seeing how this elegant flow works in a real-world application. This is where it all clicks.
Here it is, the whole story in one diagram. It starts with the measurand, the physical water level in a tank. The sensor, in this case a pressure transducer, converts that water pressure into a raw analog signal. That signal then goes through conditioning, where it's all cleaned up and amplified. The ADC then converts that clean voltage into a binary number. And finally, the processor takes that number, calculates the actual water level, and sends it to the final application, an IoT dashboard you can check right on your phone. From a physical property to an app, that is the complete journey.
And that brings us to a final, bigger thought. We have successfully covered our world in this new layer of digital senses that are constantly feeling, watching, and listening. But you know, this is just the beginning. The real question for the future is, what will we ask them to feel next? What new senses are we going to give our machines? And what new worlds will that open up for all of us? The possibilities, they're truly endless.